Question. As a professor, after a lecture starts, are you able to lock the doors?
Yes and no. Good morning, everybody. We have to talk about something very important. History was made this weekend. Absolute bonkers. Make this go away. Okay. Engineers everywhere rejoice because something that they said was impossible 5 years ago just happened yesterday.
3, 2, 1.
So that rocket is twice the height of a space shuttle. It's bigger than the Saturn V, which is the rocket that took us to the moon.
We have liftoff.
The width of that rocket is about the size of this room,
Pitching downrange.
and it's like 24 stories tall or something like that. It's huge. The largest rocket ever launched by human beings. 33 engines pushing that thing up.
I've ever seen in my entire life.
So the booster separates from the Starship. The booster turns around, comes back,
Coming in, see how fast this vehicle is moving on the left hand.
and we've seen SpaceX do this with little rockets.
Landing burn, 13 engines.
Booster running current shutdown.
Micadilla has popped his trip.
At the launch tower.
What an incredible feeling! Wow.
I don't know about you, but we're losing our stuff up here.
The future is here, now. That is how we are going to get to the moon again. It's how we're going to get to Mars. It's how we're going to put a lot of stuff in orbit. Like, experts in rocketry said that this was not possible. Like, you couldn't catch a rocket. You couldn't catch a rocket. They said you couldn't land rockets, number one, and then SpaceX did that. And now SpaceX is catching orbital boosters out of the air? I mean, granted, they only did it once. But come on, first try? This is the third flight of a rocket like that. The first flight ended in disaster, a rapid unscheduled disassembly, or RUD is what SpaceX calls it. It got up to about 90 kilometers. They had to blow it up. It blew up because it was spinning, and rockets don't fly like this, okay? The second one was successful, but they didn't land it on the tower. They landed it in the middle of the ocean somewhere because they wanted to make sure nothing would get hurt, right? They landed that booster came in, touched down on the water to within 1 centimeter accuracy of where they wanted it to be. Like, it's 9 meters across, right? And they got that thing to within a centimeter of where they wanted it to be. So third flight, they just caught it out of the air.
Does the improvement in the accuracy also improve our landing accuracy on the moon? Because I know beforehand it used to be like.
No, like hyper accuracy. So the pointy end that continued on, like this is the big deal, right? The other big deal is that the Starship flew on its second ever orbital flight. First one ended with it mostly burning up in the atmosphere. There was a lot of burn through on one of the flaps. And it landed in the middle of the Indian Ocean. The second one was targeted to land in the middle of the Indian Ocean. It survived re-entry pretty good. There was still a little bit of burn through, so they got to work on their thermal protection. But when it landed, they had a buoy sitting there in the middle of the Indian Ocean to video the landing, and they got Starship to within, I think it was less than a meter of where they wanted it to be. This is, nerds and engineers everywhere rejoice. Like this, I know that there is a lot of terrible things happening in the world right now. But there are a lot of really, really good things happening in the world. This is one of them, where humans have come together to do the impossible, right? You don't know what's possible until you try. and you're in majors that work and fight towards bringing the best of what humanity has and putting it together. Now, of course, that engineering and that science can be put to uses in war or other places. But a vast majority of our applications improve our existence here on this planet. It causes problems. We cause climate change, but we can also fix it. And so when people ask me, Mr. Bale, how can you be so stinking happy? Right? Why are you upbeat about the future? Well, I work with the future, number one. Like, my job is training future engineers and scientists and things like that. And so I see you, and I see your commitment, I see your dedication, and you become people like this. Now, are you going to work for SpaceX? I don't know. Go work for SpaceX, right? I don't care. But wherever you work towards making things better than they are right now. That's the goal. We're going to Mars. It's going to happen. Notwithstanding how absolutely crazy the guy that runs this thing is. All right. So, wanted to show you that. Let's get rid of that. Make it go away. And then bring this back. Okay, so now we're going to talk about how to build a rocket. No, now we're going to talk about all the things you need to know in order to be able to get to the point where you can build rockets. What were we doing? We were doing magnetic fields, right? And we were doing this. How do you take something that is inherently three-dimensional, right? Like a cross product, okay? And bring it into paper, right? Now my colors may be wrong here, right? But if we do let's see, does this work? No, this doesn't work, okay? So I can't get the colors right. But if I've got force, I got velocity. How do we do right-hand rules again? Do you remember? It's a shape, right? Like I call it the handshake, right? But this force, right, is equal to Q, which is just a number, times the velocity crossed into the magnetic field. So if my velocity, right, is going up, the x's mean what for this magnetic field? Into the page. So I shake my hand up, I rotate my wrist so my finger's going into the page. Which way is the force? It's to the left, right? So if I go velocity up and then magnetic field into the page, I should get my force going that way. So this is all wrong. No. I'll get it eventually here. This thing, is that no. There we go. Okay, here's my magnetic field. I should have done it in blue. There's my velocity in red, and there's my force, right? So it can get kind of awkward to walk around with things like this. Okay, doing your homework, all that kind of stuff, right? So what do? Well, you've got your hand, which is why we use the right-hand rule. You've got, I had a student once who had a disability. His forearms didn't have the right number of bones in them, and so he actually couldn't rotate his wrists. Right? His wrists were more or less locked into a certain position, and when he rotated, he had to kind of rotate his whole arm up and down to get rotation. So it was really difficult for him to get that rotation out of his hand. And so he came to me, he's like, Mr. Bale, how do I do the right-hand rule? I'm like, good question. So what we ended up doing for him is we took an eraser or a piece of clay or something, and I let him use it on the exam, but basically he's just stuck 3 pencils, right, into this piece of clay, and then with his fingers he was able to kind of rotate around one of the pencils, and he had his 3 directions, right? So there's lots of different clever ways that you can sort of visualize what's going on with right-hand rules, because right-hand rules are cross products. Cross products are these things which take 2 vectors that are, perpendicular to each other and find a third vector that's mutually perpendicular to all of them. There's other ways to do it. I did this as an experiment one time. Let's see, where did I put it? Put it right there, okay? I didn't make this. A friend of mine who knows how to use Blender better than I do made this for me, okay? And I threw it up on GitHub. So basically, it's like a 3D version that you can just kind of play with your finger, okay? And get an idea right, of what it looks like from different angles. It's not perfect. You can't like push it all the way around in some cases. But the other thing I did with this, I had way too much fun with this. See if I can get it. So it should attach. Oh, yeah, it attached all right. Okay, and we need to make it a little bit smaller. Okay, but now in augmented reality, right, you can get down. So you can be really weird while you're doing your homework, I guess is what I'm saying, right? Okay, so there's all kinds of different things out there for you to do and try, and so on and so forth. To do the augmented reality thing, you do need a device that supports, either a Google device or an Apple device that supports the camera on the back that can read its 3D space, right? But I'll put the link up on Canvas for you to, if you want to play around, just to give you, again, some ideas about how all this is working. But in the end, we do have to get this three-dimensional picture back into a two-dimensional space. So let's practice just a little bit more. It just never hurts practicing. So you guys are in the driver's seat now. Okay, we're going to practice this. So what do you want to give me first? Force, velocity, or magnetic field? Force. Okay, so give me, what direction is the force going? Up, down, left, right, in, out. Down. So force on a particle is down. Okay, now pick one of the other things. Either velocity or magnetic field. Magnetic field. What direction is the magnetic field? To the left. So we have magnetic field going to the left. So now we apply the right-hand rule to this. Okay? So I take my hand. What am I supposed to do first? It's supposed to be V cross B equals F, right? Where your handshake is V, and B is your bent fingers, and your thumb is the force. So here I have to kind of reverse engineer my right-hand rule, don't I? So I have to come in, I say, okay, well, I know that my F has to be down, right? So my thumb has to point down. I can hold my wrist either like this or like this, right? Okay, so my thumb has to point down. But how do I get my fingers, which are supposed to be in this position, to point to the left? Well, like that, right? My thumb has to be down. My fingers have to be pointing to the left. So how do I figure out which way the velocity is going? I straighten my fingers out. Normally I would go V. I would shake in V and then rotate my hand into B, and my thumb would then tell me the force. But here I was forced to do force and magnetic field and then straighten my fingers back out again. If you're using the other one with your fingers like this, right, you just turn your thumb down, your middle finger's pointed in B, and then your index finger would be pointing out of the screen. So how do I show a velocity pointing out of the screen? It's just a dot, right? For that arrowhead coming out of the screen. Okay, force, velocity, or magnetic field? Which one? And what direction is it? We did force before. Okay, which way is the force going? Up. Okay, velocity or magnetic field? Velocity, which way is it going? To the right. Which way? So what's the thing that's missing? Magnetic field. Just by looking at the force and the velocity, you only have two choices now as to which direction the magnetic field is pointing. Which direction is perpendicular to both left and right and up and down? In or out. So we know our hand eventually, our fingers for the magnetic field have to be pointed in or out, right? So if we don't get in or out, we're doing something wrong. So what do we do with our thumb? Goes up. What do we do with our fingers handshake out? It's got to go to the right. Thumb has to be up. And so that leaves magnetic field pointing which way? Into the screen. Like my fingers come around and bend into the screen. So how do I show the magnetic field goes in? I would draw it right on top of those vectors, but I want to be a little bit clearer. Okay. In or out? In. Force, velocity, or magnetic field? Velocity. Okay, so my velocity is pointed into the screen. Now, give me one of the others. Tell me the direction. Magnetic field pointed. Okay. There's a downish magnetic field. Okay. So, what direction is the force? Okay. What direction is perpendicular to both in and out and that diagonally downy thing? It's going to have to be along that line somewhere. Because that dotted line is perpendicular to the red and in and out of the screen. So I know that's kind of where I have to end up. So what do I do with my right hand rule? Which way do I shake? I go into the screen for V, right? And then I have to rotate my wrist so that I can, so I'm going into the screen, and I got to rotate my wrist so that my magnetic field can point diagonally downwards in the southwest direction, okay? Like that. And now my thumb is pointed which way? Upwards, along that line I said that it had to be. And so that would be the direction of my force. Practice, practice, practice. Make flashcards, quiz each other, do something, right? You want to have like 20 or 30 of like these laid out. Okay, and if you're not sure if they're right, just let me know. I had a website, but it seems to be moved or taken down. I got to try and find it. It was like a quiz site that just kept showing you different pictures, and it was multiple choice about, pick the direction, and you could apply right-hand rule and get practice with it. I'll see if I can try and find that again. But you want to practice. We use this skill a lot, this right-hand rule skill a lot in the form of the cross product. And we're going to use more like them as we move forward. All right. Oh, yeah. Forgot about these videos. 28. There we go. Oh, computer, why do you do this to me? All right. There's it right there.
We'll use this electron beam tube to demonstrate the deflection of electrons in a magnetic field. An electron beam running between these two terminals glances along a phosphor screen, which shows the path of the electrons by the green glow where the electrons strike. If we place a horseshoe magnet over the tube with the north pole closest to the camera, the beam is deflected downward. If we reverse the magnet, the beam is deflected upward.
Do charges experience forces from magnetic fields? Right? That current, right, was a bunch of charges. And they felt that. Ooh, don't know. Not yet. Quiz coming up. Where is, oh, there it is. So let's talk about what's going on here. I'll draw right on the screen. So we had a beam of electrons going that way. There was their velocity, okay? And then they said that there was what did they say at first? The north pole was pointed towards the camera, or was closest to the camera when that magnet came in? Okay, so if the north pole is closest to us, that means the south pole was on the other side. Which way was the magnetic field pointed, into or out of the screen? Near the thing. So we have like a north pole here, and then on the other side we have a south pole. Magnetic field lines come out of north and into south, right? So that magnetic field was pointed, I'm running out of colors, So there's my magnetic field. What direction is the force on this beam of electrons? V to the right, B into the screen. Force was up. Did anybody notice which way it bent first? It went down first. We either did something wrong or something's broken in the universe. Yeah, it's the electron that's broken. What's wrong? They're negative. The right-hand rule is defined for positive charges. So if you have a negative charge, what do? Apple, get out. Apple, no, I like Apple. Apple can stay. Apple said, use the left-hand rule. Okay. I have personal problems with the left-hand rule. Most of them come down to my dyslexia and not knowing like right from left or up from down. I've noticed besides my own personal issues with not knowing what directions are, I've noticed in my career that as soon as you teach the left-hand rule to students, there is eternal confusion over which hand to use in any given situation. So I've found that standardizing on right-hand rules only is the safer bet for the majority of people. I'm not saying the left-hand rule doesn't work. It works, okay? I'm just saying that if you start introducing more handed rules, you are going to run into problems. And this is where left-handed people have the advantage. Why do left-handed people have the advantage here? They're naturally left-handed, which means they are writing with what hand? Their left hand, right? Which comes with all sorts of problems, right, lefties? Whatever it is you have to do to not smear the whatever, right? Or your teacher's hitting your hand telling you can't. Hopefully you didn't have teachers that told you couldn't write with your left hand, okay? But they're writing with their left hands, which means their right hand is free to do what? The right hand rule. Okay? All right, right-handed people, 90% of you that exist in the world. Okay? What's your problem? You're writing with your right hand, right? What do you have to do to use the right-hand rule? You must put your pencil down. How many times in an exam have I caught right-handed dominant students using their left hand? How easy is it to be sitting there writing and then just put, right? It's rough. I would encourage you to ignore the left-hand rule, okay? Even though it works, you can use it for electrons or negative charges, whatever. My advice, take it or not, you can be safe or not, it's up to you, okay? Is always use your right hand. Just be consistent, always use your right hand. And if a negative charge is involved, what you do you know the velocity of the electrons, you know the magnetic field, you know the force is supposed to go up. The last step for a negative charge is to do what? Flip the direction by 180 degrees. Again, I've just noticed over the years that a majority of students struggle less with flipping the hand over at the end for a negative charge than doing a left-hand rule. Okay? So again, it might be different for you, and I'm not going to mark you down for using a left-hand rule or anything like that. It's just if I see you using your left hand, I will call it out. Right? I'll be like, did you mean to do that? I've walked up to students during an exam and I've leaned over them and I'm like, are you okay? And they're like, what do you mean? I was like, you were using your left hand. They go, I was? Yeah, you were. Put your pencil down, use your right hand. Tattoo or something so that you can tell the difference. Okay? Post-it notes on the day, whatever. Okay? One of the preeminent philosophers of our day. Master philosopher of thought and human ingenuity. His name is Winnie the Pooh. Said, and I quote, "I have no trouble telling my right paw from my left. It's knowing which one to start with that makes all the difference." Think about that. There's some deep wisdom there. Deep. All right. So, negative charges, use your other hand. Quiz. All right. Current carrying wires. Woo. Let me, I'll just give this to you without proving it first, and maybe we'll get to the proof later. All right. Here's a problem. We know force is a vector, right? And we know magnetic field's a vector. But the question is current or length a vector? It's length. Current's a scalar. Okay? The length, though, can be a vector. How can it be a vector? So this is a cross product, right? Let me try to show this to you by drawing sort of a what if here. Okay? Let's say that this is a magnetic field in the plane of the page, right? And it's a magnetic field like everywhere. I'm just drawing a few of these field lines to give you an idea that it's uniform and exists all the way around. Okay. And then let's take a wire. Okay? And I'm going to make this wire shape something like that. Okay? And I'm just going to say that it starts at A, it ends at B, and it does this funny wiggle, and the current is flowing from A to B. Just kind of doing a what if here, right? So the force so why do currents experience forces? Because current is charge, right? Like it's a train of charges all going in the same direction, right? So if individual charges experience forces from magnetic fields, it stands to reason that if we add up, right, all those charges we have, and we define that current, then boom, we should be able to have a force on a current. That's where that comes from. Okay. But it's a cross product between some length and this magnetic field. Now, in order to find what I drew there, what do you think we might have to do with that length? Ooh, did I hear the I word? Integrate? So what would I integrate? I could find little pieces of the force, right? We're going to find the force by adding up all the little pieces of the force. But I got to find out what the little pieces of, right? Force is going to be little pieces of the force, right? And then what does a little piece of the force look like? Well, am I taking a little piece of current? Or am I taking a little piece of wire? Yeah, it's this length of the wire. So this would be current times some, I'll just use S, L, S, doesn't matter, crossed into our constant magnetic field, right? So we're going to break up this current into lots of little ds's. Just kind of add all these little ds's up as we go. But at every point, we have to integrate a cross product? Ah? How many of you integrated cross products? One of the established methods we have in physics of dealing with things like this is to not do them, right? Is to let mathematicians deal with it, right? But it goes deeper than that because we are not going to do that integral. We're going to be clever instead, right? Because what direction does this force point? Like in this example here. We'd have to do a right-hand rule at every single little ds along the way. Okay, so let's do a few, right? Starting at A, the current, the length, the direction of the wire is up. The magnetic field is to the left, right? So which way is my thumb pointing? Into the screen. Okay, so now I go up over this curve. Now my wire's pointed this way. My magnetic field's this way. Which way is my thumb point? Still in, still in, still in. No matter where I start, everywhere along there, what direction do I get? I get into the screen, right? So I'm confident that my thumb will be pointing into the screen along the entire length of that wire, which means that I can, I don't know, it's not a cheat so much as it is a definition that the magnitude of the cross product is equal to magnitude of first vector times magnitude of second vector times the sine of the angle between them. We talked about this on Wednesday. Okay? So the right-hand rule often allows us to not formally do the cross product in the sense of that whole matrix thing, right? Instead, we can find magnitude of it, magnitude first vector, magnitude second vector, sine of angle between them, and then use the right-hand rule to give us the direction. We know the direction is going to be into the page here for this wire segment. Okay? It's just a question of what's its magnitude now. Well, now I have to integrate this ds sine theta, which means I need to get the length of my wire in terms of theta and all that kind of stuff. Well, actually, no. I can even be a little bit more clever about this. Don't worry, we only have to do this once. Do this once, we won't ever have to do this again. Okay? Be a little bit clever about it and realize what happens when your magnetic field and the direction of the wire / current is in the same direction. What's the angle between those two vectors? 0, right? We're only going to pick up components of this sine theta thing in here, right? Only picks up magnitude when the wire and the magnetic field are perpendicular to each other. Like when sine is not 0, it's got to be anything besides 0. Well, if you do that, you'll find out that the distance that matters is the straight line distance between the 2 points. That wire can do whatever it wants to do. Heck, it could come down and do loop-de-loops, getting to B. And what would be the only thing that matters? The actual straight line distance in the field between points A and B. Which is why you'll kind of often see this written as, well, the force, okay, magnitude is going, magnitude, not velocity, come on, go away, is equal to IL prime cross B. They'll write it like that, where this L prime is really just the straight line distance between the two ends of the wire in the field. If you can find that, you don't have to do this integral. The sine theta is going to take care of everything for you. The right-hand rule is going to give you the direction that's going to be pointing. And quite often, we don't care what direction it is. All we care about is the magnitude, in which case it's just going to be ILB, IL prime B. Okay?
So are you doing cross product again?
No. Because the answer you're going to get out of that is if we do this purple one, the force will be ILB sine theta, where like theta is that angle, right? So, and then you just right-hand rule, you can find the direction. Okay. And what if A and B were like right on top of each other and the distance was making a right angle with the magnetic field? What would your answer be? ILB. Because what sine of 90? 1. Okay. So that thing in the box is really what we use. It's just if your actual wire, right, isn't a straight wire, if it's some sort of curved wire, ignore the curve. Just look for the two endpoints. Your new length of the wire is whatever the distance is between those 2 points, whatever angle it has with the magnetic field. That's the only thing that matters. The integral takes care of itself, which is really quite magical and useful. Okay, let me show you a couple more videos so you can see that these forces are a big deal. She look like she enjoys her job?
We'll use a large horseshoe magnet and a current-carrying wire to show the force a magnetic field exerts on a current. The wire is placed between the arms of the horseshoe magnet.
Ooh.
Then 20 amps is run through
That's
the
a lot
wire
of current.
in the direction shown
Whoa.
by the arrow.
Freeze
The
frame.
wire jumps out of the magnet.
How big a force is this? It's big force. Big force. Do it again. Do it again.
This diagram shows the directions of the current, the magnetic field, and the force on the wire as predicted by the right-hand rule.
It works.
If we reverse the magnet and run the same current through the wire, what will the wire do?
Okay, so our right-hand rule was such that we had the current going in, which is the direction, right, of the first vector, and then the magnetic field was to the left, okay? And so the thumb was up, which means the wire jumped out, right? It was a pretty big force, like that thing went flying, right? So if we reverse the direction of the magnetic field, the current stays the same, but now the fingers are this way. Which way is the thumb pointing? Down. So what's this going to do? It's going to push down. That's not very exciting.
This time, the wire doesn't leap out.
Okay.
The magnetic force on the current now pushes the wire down.
You can kind of see it deflecting, right? It's not going to jump out. What did we just make? What kind of thing in your life, when you give it electricity, moves? Car? Electric car? What was this? The very beginnings of an idea. What's that idea? A motor. Yes, no? It didn't look like it, right? It's just a wire jumping out of a magnet. But if we can get that motion to repeat itself, right? If we could have the wire jump and then jump again and then jump again and then somehow harness that force of that push on that wire, that's a motor. So now we have to talk about loops. Everybody's favorite. Yeah, that one. Switch back. There we go. All right, so how do we talk about loops? We did those videos. Here we go. Loop of wire. Okay. Let's, I'm going to do example. This will be an application of how to find the force on things using right-hand rules and all of our equations and stuff like that. So what does my wire look like? It's going to be a semicircle. So there's a straight path and then, that wasn't very good at all. That wasn't, you know what? Do this first. And then draw this. There we go. That's still not good. Okay, that's fine. And then, so there's our wire. It has a radius of r around the semicircle. And we're going to run current in this thing such that current flows in the bottom straight segment. It flows from left to right. And then it's going to flow in a counterclockwise direction around the curvy part. And what we're going to do is we are going to find the force on that wire if we have a magnetic field. We'll do it in purple. That points upwards in the plane of the page. That magnetic field isn't just where I drew it. It's just to keep we'd have to draw these magnetic fields like everywhere like this, right? And now the drawing has gotten really messy, hasn't it? Okay, so we just sort of indicate, yes, magnetic fields pointed straight up, but that's like everywhere. We're just not going to draw that. Okay, So now what we're going to do is we are going to find the force on this whole loop. Okay? Now, to do that, we either rip out an integral and go for it and bang our heads against a integral with a cross product in it, or we get clever, right? And we think about like endpoints and all that kind of stuff, right? So let's be clever. Let's do the I'm going to break this up into two segments. Okay, I'm going to call segment 1 to be down here, this flat segment, this horizontal segment of my wire, and then I'll call segment 2 to be the half circle part of my wire. Okay, so for this is going to be I times L1 crossed into my magnetic field. Okay, so what I don't want to do is any cross products, so I'm just going to write this as I times L1 times B sine theta. That's, again, magnitude of a cross product. And what do I know here? So do I know the length of my first segment here? What is it? From there to there. Yeah, that's going to be twice the radius of this circle, isn't it? Okay. So I got I times twice the radius of the circle times whatever my magnetic field strength is. And okay, and now sine of the angle. What's the angle between the magnetic field and L1? 90 degrees, right? B is vertical, the wire is horizontal. So what's the sine of 90? It's 1. So this is 2IRB. What direction is that pointing? You notice I stripped off the vector direction and went straight for the magnitude. How do I find the direction? Right-hand rule. So which way do we point our fingers? So we start with L crossed into B, right? But the direction of L is the direction of the current. So the direction of the current is to the right. My magnetic field is pointed up, so I had to rotate my wrist around, and now my thumb points which way? Out of the screen. So this is 2IRB out. Often, so if your positive x is to the right and your positive y is in the plane of the page upwards, then positive z is which way? Yeah. Your k-hat direction will be out of the page. Okay? So sometimes out is referred to as positive k-hat. Okay, now we've got to tackle the semicircular portion. Okay? Which means we do bad integral, or we remember that all we really need is the distance between the endpoints. So for this semicircular portion, I'm going to go, so F2 here, right? I'm going to go from that point, let's call up that point A, over here to point B. Now I can work my way around the semicircle, or we can take what we did back here to heart. All we really need is the straight line distance between those 2 points, right? Okay. So what's that distance? It's IL2B sine theta. That's I times 2R times B times the sine of, what's the angle? Nope. It's just 90. Because the 2R, the distance from A to B is perpendicular to the magnetic field. So this is just going to be sine of 90 degrees. So magnitude-wise, I get 2IRB, like I did before. But what direction does this point? We either can follow our way around the semicircle, realizing that at point A we start going up and the magnetic field is up, so the force there is 0. But as we come around and our current is flowing to the left at the top, and then my magnetic field, so my thumb's pointing in, no matter where I am on that curve, I'm going to end up with my thumb pointed in. Or I can do L2, which L2 is going this way, my L2 prime, okay? It's going that way. And so I would have fingers to the left, magnetic field up, thumb is pointing into the page. So the blue one, same magnitude, but into the page. So when we put the two forces together, what do we get? I just came up with a really fancy way of writing the number 0. What is the net force on a closed loop of wire? A wire loop that starts and stops on itself. It's 0. I can do this with any shape, and we would still get 0. Because a loop of any shape, I don't know, that shape, has an effective length of what? What is its beginning to end distance? Any shape. So any closed loop in a magnetic field experiences 0 net force. Individual parts of the loop can experience different forces. But the net, the overall sum of forces, is going to be 0. That's amazing, right? Because 0 is easy. The force might be 0, but the torque is not. Let's take a square. We're going to do a square loop because squares are, well, sort of, I mean, it's not square, like rectangular, right angles, that sort of stuff. Okay. And then we are going to take a magnetic field. And again, this magnetic field is going to be everywhere in the plane of the page. It's just going to be pointing to the right everywhere. Again, I'm not drawing all these magnetic field lines. It's just that magnetic field is everywhere. Okay, and then I'm going to label the segments. 1, 2, 3, 4. All right, and then my current is going to be flowing counterclockwise around this loop, okay? We already know that the net force is what? We know it's 0. But let's, for the sake of being able to practice and making sure that the physics is all right, let's apply some right-hand rules. Let's add up the forces on all these segments, okay? So let's look at segment number 1. What is the force on segment number 1 if the current is to the left and the magnetic field is to the right? Why is it 0? They are anti-parallel to each other, right? They're in the same direction. And what happens to a cross product if you have no perpendicular component? It's 0. What's the sine of 180? It's 0, right? Just like the sine of 0 is 0. So segment number 1 and segment number 3 will have 0 force on them because there is no perpendicularness there. So the cross product itself works out to 0. So 1 and 3 are 0. Okay. So let's take a look at number 2. So now, do we have perpendicularness? Yeah, we've got a current flowing up and a magnetic field flowing to the right. So we take your right hand out. What do? How do we shake? Up or down? Up. We're on segment number 2. Current's flowing up there. Rotate wrist to get magnetic field at 90 degrees. Which way is thumb pointing? In. So the force on segment number 2 is pointed inwards. Okay. What about segment number, and not 0, but segment number 4? What can you tell me about the magnitudes of the force on segment 2 and segment 4? Same length, same current, same field, magnitude same. Okay? We know it has to be magnitude same because we just proved that any closed loop has a total net force of 0. So we can argue this several ways. We're going to do right-hand rule, but we're also going to use our brains. If the net force has to be 0, and I have a force pointing in on one side, what direction does the force have to point on the other side? Okay, good. Let's make sure the right-hand rule proves it. Which way do I shake? Down. Magnetic field to that way. Which way is thumb pointing? Out. So indeed, F4, where F2 and F4 have the same magnitudes. Notice I didn't put any vector signs over the top, right? But they have opposite directions. Means that when we go to add up all the forces on this loop, we get 0, right? But the torque here is not 0. And now we have to do a trick, a mental adjustment to how we are drawing this diagram. And so to do that, I brought with me my trusty coat hanger that I have bent into a sort of square. Okay? So we are currently looking at the square like this, aren't we? What I am going to do is I am going to take this square, I'm going to rotate this picture. I'm going to rotate it so that the bottom of my loop will be pointing at us, out of the page, out of the screen. So I'm taking this loop and I'm going to turn and I'm going to draw the picture this way. Okay? So I'm going to take this entire picture and I'm going to rotate it out like this. So what is the loop going to look like when I do that? It's going to just look like a line. Isn't it? The magnetic field, when doing that, does not change its orientation. Whether the loop is drawn like this or the field going this way, or I draw it like this, the field still goes this way. Okay? What direction now would I be drawing F2? So here's F2. It's pointed downwards in our diagram, right? So it's pointed in, right? I just gave the answer away. And I rotate the whole thing like this. Which way is it now pointing? Down, right? So I've got a force, F2, that points down. So therefore, what direction does F4 point? It points up. If I define an axis of rotation along my loop, like I somehow suspend my loop on a rod so that the loop is free to turn, right? Or rotate around that axis. What can you tell me about the torque? What direction will F2 cause this thing to want to change its motion? Clockwise or counterclockwise? Clockwise, right? And the way you do that, lots of ways. You can use cross products, other right hands. You can grab your pencil, hold it on the axis of rotation, and then just pull it in the direction of F2. Which way does your pencil rotate? Clockwise, doesn't it? Okay? And then you do the same thing for the other one. You, again, grab it where it's articulating, and then we apply a force up, right? Okay? And it would still cause a clockwise rotation, wouldn't it? So both of these torques are in the clockwise direction. They both want to rotate this loop clockwise and cause this whole thing to spin like this. Does anybody remember the symbol for torque? Tau. Oh my gosh. It's Greek. It's Greek everywhere. Tau, the torque, okay, is found, the torque on a current loop is found by taking the current, multiplying times the, area. I don't know why my pencil is being weird. Crossed into the magnetic field. This is area of the loop. Okay? B is the magnetic field, I is the current. Generally, okay, let's stop. Let's just stop. Area. Vector, scalar, or elephant? Oh, okay, good. You remembered. Right? Area is a vector. What direction does the area point? Yeah, if I'm finding the area of my desk, right, and I want to find the direction, the orientation of that area, what direction is it? Perpendicular to the surface of the area itself, right? But unfortunately, this loop, we could define like an area vector that points that way or that way, right? Perpendicular is two directions. So how? Isn't it bad enough that torque has been introduced? You having the PTSD from torque in Physics 4a? Remember all that rotational stuff, angular momentum? Yeah, it's bad. My 4a students are about to go in it. They have one more day of conservation of momentum. And again, of course, they're thinking that's hard. So what do we do? What do we do? What do we do? What we do is we define something else. Okay? It's physics. Just define something else. We're going to use a different Greek letter, okay? And this is called the magnetic dipole moment. It is the current times the area. And you're like, well, Mr. Baylor, what does that get me? What it gets you is I can now write torque as mu cross B. I love physics. But now what do I do with directions? And the answer is there is another right-hand rule for this. Like, Mr. Baylor, this isn't any better. We define the direction of area in current-carrying loops and magnetic fields by looking at their magnetic dipole moments, this mu character right here. And so to define what this is, say for this loop, this is the right-hand rule you are going to employ. And this right-hand rule is going to carry us into next chapter, believe it or not. So I've taught you the handshake right-hand rule, okay? Which again, I think you guys told me that Dr. Kerfoot did it like the handshake, right? You can also learn it with the index fingers. But that always gets your hand in sort of this, it starts with some sort of flat finger palm shape to it, okay? Which is very different from the other right-hand rule that you may or may not. Did Dr. Kerfoot tell you about the right-hand rule for like angular velocity, Physics 4a? Where you curl your fingers around and your thumb points in a direction. I like to call this one the hitchhiker. See how your hand is in that hitchhiker form, okay? Where your fingers are like curled into your palm, right? The hitchhiker starts with like this shape right here with curled fingers and a thumb outstretched. The handshake starts with these straight fingers, right? I'm going in a current, I'm going in a velocity. Whereas we curl around with fingers and then our thumb extends. In the case of the magnetic dipole moment, you curl your hands around in the direction the current is flowing. So on my left-hand picture here, which way is my current flowing? Clockwise or counterclockwise? It's a counterclockwise flow. So I will take my hitchhiker, wrap my fingers around counterclockwise, and which way is my thumb pointing? It's pointing out of the screen. So I could indicate my magnetic dipole moment with like a dot right there, right? There's my magnetic dipole moment. So in the shifted picture where I've tilted the bottom here, we can either sort of visualize how that changes, or we can take a look at which way the currents are flowing. The current is flowing out of the screen on the left-hand side and into the screen on the right-hand side. So the circulation is one of my hand has to circle around in like a horizontal plane where fingers are coming out of the screen on the left and then turning around and going into the screen on the right. Which way is my thumb pointing? Upwards. So the magnetic dipole moment of this loop is pointed upwards. Either out of the screen or up. You can do it both ways. So what does this get us? Okay. What is the angle between mu and b right now in the picture I've got drawn? It's a 90-degree angle, isn't it? So what will the torque on this one be? Then the torque is going to be mu times b times the sine of 90, which is 1, right? And then I know that this is going to be IAB, right? That it's not direction of area. It's really, we're kind of cheating today, right? Like I keep saying it's a length vector crossed into a magnetic field and an area vector crossed into a magnetic field. But we're really kind of defining what directions L and A point by the current direction. Nodding and winking and going, yeah, we know current's a scalar, but really it's got direction associated with it. So we borrow. So rather than worrying about which way A is, we look at what our currents are doing, and we use this second right-hand rule to define the direction of the current with respect to the area. So the torque is a maximum right there, isn't it? Okay. So what happens when the loop rotates, right? And say the loop gets to the orientation like right here. Magnetic field. So it's rotated around in the clockwise direction. It's gotten to this point, right? So what direction is the magnetic moment of this loop now pointing? Here's my magnetic dipole moment. Okay. What's the angle between the magnetic field and the magnetic dipole moment? 0. Okay. So if the angle is 0, then the torque is 0, isn't it? Which way do the forces point? They don't change their directions. The direction of that force is dictated by the current and the magnetic field direction, right? Has the current and magnetic field, have they gone out of the 90-degree angles that they're at just because this thing's rotated that way? No. Current is still flowing, in this case, out of the screen. Magnetic field is still pointed to the right. Current, right, my thumb is still up. And I can do the same thing down here. Current into the screen, magnetic field, my thumb is still down. The direction of the force doesn't change. But the magnitude of the torque does. Because how much torque is on that loop? 0. The forces are not perpendicular to the axis, they're parallel, right? So what is this loop going to do eventually? Now, it does have mass. So if we put it here and we let it go, it's going to rotate, right? And then it's going to get to 0 torque, but it's going to have momentum, so it's going to kind of go, right? But as soon as this magnetic moment gets below the horizontal, we now pick up torque in the opposite direction. And so it kind of will wiggle back and forth until it pins itself straight up and down. If it had no mass, it would just go and just stop there, right? Okay? So we haven't quite gotten the rotation that we're after to make an electric motor, have we? We're almost there. Can you see what has to happen? What has to switch? Oh, we could switch the external field. For every, like we want maximum torque there, but we know the torque's going to go to 0. So as soon as it gets to 0, we switch like the magnetic field so that there's now torque applied so that it keeps rotating. Well, it turns out it can be pretty difficult to switch the magnetic field. But we can switch the direction of the current. If you switch the direction of the current at the top here, and this thing has mass and it keeps moving, and we switch it so that the torque continues on in the same direction for that half turn, and every half turn of the loop we manage to switch the current back and forth, we can keep this thing going in one direction. Math in this class? Nah. We do physics instead. This, like, torque is involved now. Timing is involved now. Okay? Yeah, this is gonna go weird. So what we're actually going to do on Wednesday is we are going to do a little bit of a tangent. All the chemists in the room are going to get really excited because we're going to talk about the mass spectrometer. We're going to talk about the mass spectrometer as an application. Okay, maybe the chemists aren't going to be excited. Maybe they're going to be angry. But we're going to talk about how a mass spectrometer actually uses everything that you've learned about charges and magnetic fields to do what it does. And then we're going to move into the next chapter where we're going to actually talk about where magnetic fields come from. And eventually we're going to put this all together to make a motor. So we're going to kind of park torque for right now. You'll have to be able to calculate it for your homework. But we're going to come back to deal with all of the yuckiness a little bit further on down the road. You still don't have your lab packets, right? It's because your teacher's an idiot. I hopefully will have the lab packets for you tomorrow. If I don't, it's okay. We can still do the lab, and we won't even have to do it together. But the lab packets are being, hopefully, fingers crossed, printed today. So I'll have them for you tomorrow. Tomorrow's not a lab. Tomorrow's the autopsy. We're fine. I'm fine. You guys are, I don't know what you guys are. We'll see you tomorrow for the autopsy.